Okay. Hi, everybody. Right. Since you've been talking quite a bit about white blood cells and immune functions, today we're going to be talking a little bit about the treatment of inflammation. So the various pathways, the various methods of how we can treat patients with inflammation. And as a part of that, we're going to be talking about the metabolism of a class of mediators of inflammation, which are called eicosanoids. Okay, so it's going to be about eicosanoids and about treatment of inflammation. So drugs, anti-inflammatory, inflammatory drugs. What is inflammation? What are the symptoms of acute inflammation, let's say? How do you know if somebody comes to you, a patient, your friend? Okay, very good. So those are the four classical symptoms of inflammation. So swelling, redness, increased temperature, and pain. Okay? There's usually a fifth one added. Indeed, so damaged function or decreased function. Right, so those are as I said, classical symptoms of inflammation. They're really classical because they come from antiquity. They were actually described by a Roman physician in, I think, 30 AD or something, or 50 AD or something like that. So very, very old. So inflammation has been recognized very long time ago as a specific entity, a clinical entity. And since people understood inflammation, I mean, it wasn't necessarily called inflammation, but because people understood it, they also looked for ways to treat it. Do you know any old or ancient or traditional ways of treating inflammation? Or, yeah? Right. Leaching? Well, yeah. I mean, leaching was a method for pretty much everything. So, yeah, I'm not sure how specific that was to inflammation, but I'm sure it would help. Definitely, yeah. Cooling down the patient or cooling down the inflamed part of the body is a very, very old method, and it's pretty much still used to some extent today. So, yeah, absolutely. Cooling down, icing is a very good method because obviously, you know, cooling down the part of the body slows down all the processes, including inflammation, and decreases pain and everything. So that makes sense. What about any pharmacological or herbal methods? Indeed, non-steroidal anti-inflammatories, but that's not really all that traditional. I mean, I was thinking more like, you know, hundreds of years ago. But we're going to be talking about those, indeed. Have you heard of using willow bark to treat inflammation? Willow, do you know willow? A tree, big tree with like overhanging branches. Willow? Yeah, I don't know. Yeah, maybe. People can translate it to your individual languages and just tell everybody. Yeah. Okay, so willow tree bark is one of the oldest willow tree. Okay, so the bark, can't see it? I'll try another one. What about this one? Just lasts for, yeah, anyway. Bark, no barks. Anyway, bark. So the willow tree bark and some other plants that in the end we found out that they actually contain similar compounds were used since a very, very long time ago. Actually, the first mention, not necessarily of willow bark tree, but some other plants for treating inflammation goes back to about 2000 BC, like Egyptian papyri. So very long time ago. So anyway, willow bark tree was a tried and true method for treating inflammation, including fever, including pain, etc., etc. And it actually went on until the beginning of the 19th century, where chemists tried to isolate the active substance from the bark of the willow tree. And the first thing they tried to isolate, or they isolated, was called salicin. don't have to remember those, okay? It's just history. Salicin. Does anyone know why salicin? Why they call it salicin? Because in Latin, willow tree is called salix. Okay? So it was called salicin. It was just a crude, stuff, which worked better than willow tree bark itself because it was more concentrated, but it actually tasted really bad. So the chemists tried to, change the chemical, try to isolate even more if they can get something, the real pure stuff out of it. And what they isolated in the end, which is like mid-19th century, was called salicylic acid. Okay, you see where the name comes from. It comes from salicin, it comes from salix. Salicylic acid. Okay, and salicylic acid in the end was found that it's pretty easy to synthesize, so they didn't actually have to isolate it from willow tree bark, which meant that it became a lot cheaper and everybody was using it to treat fever and pain and all sorts of things. Now, towards the end of the 19th century, people realized that, yes, salicylic acid is better than salicine, but actually it still doesn't taste all that well, and it actually irritates your stomach, and you had to use relatively high doses. So chemists at the Bayer factory tried to make a better salicylic acid, and what they tried was adding an acetic group. So what they created was acetosalicylic acid, which we know today as aspirin. Okay, aspirin is actually a brand name, okay, as maybe you know, maybe you don't know. So the correct generic name is acetosalicylic acid, okay. Now, salicylic acid looks like this. This is salicylic acid, and this is aspirin. You won't be asked to draw those structures, it's just so that you can see how it was derived. Okay, so a very simple change in the molecule actually led to a relatively significant increase in effectiveness. So the doses could be decreased. And also there was lower irritation of the stomach, and suddenly aspirin became probably the best-selling drug of all time, and we still use it and it still works. Okay, so the long journey from a simple herbal treatment that worked, but obviously, that there were disadvantages to it, through all the individual steps of isolating the active substance to actually chemically modifying it, led to aspirin, which is the first of non-steroidal anti-inflammatory drugs. Okay, this is a, you can't possibly see anything from there, now that I look at it. Okay, NSAIDs, non-steroidal anti-inflammatory drugs, is a group that includes aspirin and some other ones that we're going to be talking about. Why they are called non-steroidal will become clear later on. Okay, so this is the story of aspirin, but actually, even when it was synthesized, people had absolutely no idea what was the mechanism of effect. They didn't understand it. When do you think was the mechanism of effect of aspirin discovered? Just give me some dates when you think that was. So here, the synthesis of aspirin itself, I think it was in 1897, if I'm not wrong. Okay, so this is the very end of the 19th century when aspirin was first synthesized. When do you think we first understood how it actually works?
I guess in the end of the 1900s, like 1970, 80. 1970
or 80, okay. Any other guesses?
1993.
1993, okay.
40s.
1940s. Okay, well, you were actually the closest. It was early 1970s. I think it was 1971 when they published a paper which actually found out how aspirin works, which is quite remarkable considering how long it's been used. Now, and here we come to eicosanoids, aspirin was found in the 1970s and late 1960s and 70s. It was found to inhibit the production of prostaglandins. So aspirin inhibits the synthesis of prostaglandins. Now, prostaglandins themselves were discovered in 1930s in ejaculate in sperm, and they were thought to originate from the prostate, so that's why they were called prostaglandins. But later on, it was found that they are very important mediators of inflammation, and now we're going to talk about prostaglandins and other members of the group, which we call eicosanoids. Right, so eicosanoids is a fairly large group of hormones or signaling molecules. They are all derived from fatty acids. Okay, so they're fatty acid derivatives. And more specifically, they are derived from polyunsaturated fatty acids. And they're all derived from fatty acids that have 20 carbon atoms. Hence their name, because in Greek, eikosi means 20. Okay, so eicosanoids means that they are derived from fatty acids that have 20 carbon atoms. Okay, clear where the name comes from? Right. Do you know any polyunsaturated fatty acid with 20 carbon atoms? Very good. Arachidonic acid is definitely one of the sources of eicosanoids, and actually in humans, it's the major source of most of them. What is the structure of arachidonic acid? What is the systematic name of it? So this is the trivial name, but what is the systematic name of eicosanoid, of arachidonic acid? It's got 4 double bonds. Now we agreed that how many carbons does it have? It's 20 carbons, okay. So in the shorthand nomenclature, we would call 20, we would write 24, 20 carbons, 4 double bonds. So what's the systematic name of it? How do we name aliphatic fatty acids, just normal carboxylic acids? How do we call them generally? How do we name the structure? What do we base the name on? It's completely generally.
Greek numbers.
Huh?
Greek numbers, like that.
Okay, very good. Yeah, so we start with the carbon chain, and then we add oic acid. Okay? Now, you probably won't know what the carbon chain with 20 carbons is called. Okay? But it would be eicosanoic acid. Okay? Eicosanoic acid. But here we have 4 double bonds. So the saturated form would be called eicosanoic acid. Clear? 20 carbons, carboxylic acid, called eicosanoic. But we have 4 double bonds there. So it's not going to be eicosanoic acid, it's going to be... Yeah, almost. Anybody? It's going to be called eicosanoic acid. Eicosanoic. Okay, so tetraene means that it has 4 double bonds. Okay, eicosatetraene. Okay, the same way, I don't know, should I go into detail with the nomenclature? You have butane. Now, if this butane has 2 double bonds, what is it going to be called? Butadiene. Okay, so here we have eicosane instead of butane, we have eicosane. Eicosane tetraene, eicosatetraenoic acid. Anyway, let's not spend too much time with nomenclature. Right, so arachidonic acid is eicosanoic acid. But obviously, it's fairly important what kind of double bonds they are and where they are in the molecule. So first thing is, what kind of double bonds can we expect in a normal polyunsaturated fatty acid? Because fatty acids in our body or in nature actually have fairly limited kinds of structures, okay? We don't get all different isomers. Only very specific isomers really exist. So what do we know about double bonds in polyunsaturated fatty acids?
Cis.
Okay, they're all cis. Very good. What else? Is there anything about their position with respect to each other?
Come regularly or 5, 8, 11, 13, like
Okay, okay.
randomly.
Okay, they're not randomly, so they're all kind of put together, that's true. But at the same time,
It is also a single bond.
just one single bond? They're always separated by a methylene bridge, okay? So they always look like this. So there's always a CH2 group between them. Why is that important? What if there wasn't a CH2 group? What if they looked like this? What would that mean chemically? What kind of double bonds are these? They're still cis. They're conjugated, okay? But in real fatty acids, in normal fatty acids, they are not conjugated. Very important, okay? So this we practically never find in fatty acids. Sometimes you can find, but okay, those are exceptions. In fatty acids, they always look like this. Almost always they look like this. Okay, so they're not conjugated and they're cis. They always have exactly one methylene bridge between them. So that's to what you said, that they're not randomly just spread out. They're always next to each other, separated by one CH2 group. Okay. Why do I keep talking about that? Well then, if we know that they're all cis, and they are all next to each other with only one CH2 group between them, all we need to know is how many we have and where the first one is. Because all the other ones we can just calculate in our heads, because we know they will only be separated by one CH2 group. Okay, raise your hand if you understood what I just said. Good. Okay, that's, well, sort of, yeah. Okay, okay. So where I'm heading is the type of nomenclature that we use for polyunsaturated fatty acids, where the only things we need to know is how many carbon atoms the fatty acid has, how many double bonds, and where the first double bond is. Okay? Because all of them are going to look like this. Yeah? Good. Now, there are two possible nomenclatures for where the double bonds are. Okay? We can start counting from the carboxyl end, or we can start counting from the end, from the other end. Okay? Which one is the correct way in organic chemistry? From the carboxyl end. Okay? So this is the right way. So for eicosanoic acid, we would say, well, it's 24 double bonds, and the first double bond, which is usually written as delta, is on the, I don't know where it is, 5 carbon, okay, delta 5. Okay, so for arachidonic acid, the first double bond is delta 5, and all the other ones are separated by one methylene bridge, okay, one CH2 group. So this is the correct nomenclature, and actually the completely correct nomenclature would be delta 5, delta 8, delta 11, delta, whatever it is, 14. Okay, so naming actually all of them. You don't have to write this down, okay? So this is one way of naming the fatty acid. However, in the biochemistry of fatty acids and biochemistry in general, we actually use the other method, which is not entirely correct from the point of view of organic chemistry, but historically that's how it developed, okay? So we count from the other end. Now, the nomenclature, the writing down, uses not delta, but uses another Greek letter, which is omega. Okay? Meaning that we're not starting from the alpha atom, but we're starting from the furthest atom away, which is called by omega, which is the last letter in Greek alphabet. Okay? So arachidonic acid would be 24 delta 5 whatever, or we could name it 24 omega, does anyone know? 6. Okay? And this is the nomenclature that you will find in medical textbooks, in nutritional manuals, whatever. Okay? So this is an omega-6 acid, because the first double bond starts on the 6th carbon atom from the other end than carboxyl end. Okay? Omega-6. Now, the recommended nomenclature now actually uses another letter for it. So what you would find is N6. But otherwise, it works exactly the same way as omega. Okay? So if you find an N6 fatty acid or omega-6, that's the same thing. Okay? Delta is counting from the other end. Right. Well, why are these, and you've probably heard about omega-3 and omega-6. Who's heard of omega-3, omega-6 fatty acids? Okay, everybody. Okay? Why is that important? Why do we talk that omega-6 or omega-3, that we should eat them, we should eat as many of them as possible? Why is that important?
Can't make them ourselves.
Because we cannot synthesize them ourselves. Okay? The only group of polyunsaturated fatty acids that we can synthesize are the omega-9 fatty acids. Okay? So omega-9 we can synthesize in our body. But we cannot synthesize omega-6 or omega-3. Why is that? Why can we not do that? And which one is the enzyme responsible for that? How do we synthesize fatty acids? How do we synthesize unsaturated fatty acids in our body? Does anyone remember? What do we start with, and what do we do with the starting substance? It's actually fairly simple. We start with a saturated fatty acid, and we desaturate it. We insert a double bond into it. Okay? That's how we do it. And the enzymes that are responsible for putting in the double bond are called desaturases. Okay? Because what they do is desaturate. Okay? Desaturases. Now, there are many types of desaturases depending on where they insert the double bond. Okay? So we can have 9 desaturases, which put the double bond on the 9th carbon from the carboxyl end. We can have 15 desaturases, which puts it on the 15th carbon. We can have 12 desaturases that puts it on the 12th carbon. Okay? Many different desaturases. We can have 3 desaturases that puts it on the 3rd carbon, etc., etc. Okay? In humans and in most mammals, the largest desaturase, the desaturase with the largest number that we have is 9 desaturases. So the furthest from the carboxyl end that we can put a double bond is 9 carbons. We can't put it any further than that. Okay? Now try to pay attention now, because now it's going to be a step that you need to kind of imagine. Okay? Imagine you have stearic acid. How many carbons does stearic acid have? Can't really. There's a suggestion of 16. 14. 18, okay? There's 18 carbons, okay? So we take an 18 carbon stearic acid, and that's actually the one that usually we use for making unsaturated fatty acids, okay? And we use the delta 9 or 9 desaturase. First of all, what is going to be the fatty acid that we get? And what is going to be the omega nomenclature for it? Huh? It's going to be oleic acid. Okay, so we insert 1 double bond into stearic acid using delta 9 desaturase, and it's going to be omega. It's going to be omega 9. Okay, because we're starting 9 from the carboxyl, but since we have an 18 carbon molecule, it's also 9 from the other end. Make sense? Okay? And this is the furthest we can go. So we can't possibly make omega-6, because omega-6 would mean adding the double bond 12 carbons from the carboxyl end. We would need a delta 12 desaturase for that. So we can't make omega-6. And we definitely can't make omega-3, because that would mean having a delta 15 desaturase, which we don't have. Okay? So that's the reason why we cannot make omega-6 or N6 or N3 fatty acids, polyunsaturated fatty acids. We can only make omega-9. Therefore, the omega-6 and omega-3 are so-called essential fatty acids, and we have to get them from the diet. Right? Good. Now, going back to our eicosanoids. So we said that arachidonic acid is a omega-6 fatty acid. Okay? Now, either we have to get our arachidonic acid from the diet, or we can make it from another omega-6 fatty acid. So we can get another omega-6 fatty acid from the diet and then change it into arachidonic acid. Do you know which fatty acid we can get from the diet that's actually fairly abundant and we can change it into arachidonic acid? It's linoleic acid. Very good. Does anyone know what the structure of linoleic acid in this nomenclature is? Anybody? And obviously we said that it's omega-6. Okay? So linoleic acid is 18, 2 double bonds, omega-6. And this is actually hugely abundant in vegetable oils and all sorts of places. Okay? So this is our main source of omega-6 fatty acids. So what do we have to do with linoleic acid to turn it into arachidonic acid? What do we have to do?
Add 2 carbons.
We have to add 2 carbons.
And make 2 double bonds.
And add 2 double bonds. Okay? So what we do now, and you don't have to remember the details, first we add another double bond. Okay? And what we make is gamma linolenic acid, which is 18,3 omega-6. No? Now, why do I talk about gamma linolenic acid? Because it's slightly confusing, because there also exists an alpha linolenic acid, which is also 18,3, but it's omega-3. Now, can somebody explain why we could have 2 linolenic acids and one of them being omega-6 and the other omega-3? Anybody just try to wake up and... How can we have 2 linolenic acids? They're both 18,3, but one of them is omega-6 and the other one is omega-3.
Double bonds are on different places?
Yeah, we basically just take the 3 double bonds and we shift them to one side. Okay? And from omega-3 we get omega-6, from omega-6 we get omega-3. Okay? So this is just so you know that when you see a linolenic acid, it can be either an omega-6 if it is gamma linolenic, or it can be omega-3 if it is alpha linolenic. So there are 2 linolenic acids. Okay?
We need the gamma one to make the...
For the omega-6, for making arachidonic acid, yes. For making another polyunsaturated acid that we're going to mention in a minute, we use alpha linolenic. Okay? Anyway, so we have gamma linolenic acid. In the next step, we add 2 carbon atoms, okay, and we make a compound that's called dihomo gamma linolenic acid. Now, the nomenclature, I don't know if you heard of it before, linolenic. There are 2. When we talked about neurotransmitters, we talked about the preposition nor, like noradrenaline. Do you remember? Nor? And nor means that we removed one carbon atom. Okay? So noradrenaline has one less carbon atom than adrenaline. Okay? HOMO is the opposite. We added another carbon. Okay? It's an organic chemist's nomenclature. So dihomo gamma linolenic acid is going to be 23 omega 6. Okay? We added 2 carbon atoms.
Can you just repeat the name one more time?
Dihomo, H-O-M-O, gamma linolenic acid. Okay? And it's 20 carbons, 3 double bonds, omega 6. And from that, by adding another double bond, we make arachidonic acid. Okay? I'm just going to mention very quickly this other polyunsaturated fatty acid, which is omega-3 fatty acid, which is abbreviated EPA, which stands for eicosapentaenoic acid. So eicosapentaenoic acid, it's going to be, what's going to be these numbers? Eicosapentaenoic, 25, and it's omega-3. Okay? A very important part of fish oils and all the supplements that people now take is EPA, which is eicosapentaenoic, it's omega-3 acid, and it's derived from alpha-linolenic acid through a complicated process. Okay? Just an aside, in our body, we can't efficiently make EPA from alpha-linolenic acid. Okay? So if you do take alpha-linolenic, or if you have plenty of alpha-linolenic acid in your diet, we are actually very bad at making EPA. So you still have to take, if you want it, you still have to take it in a supplement. And we're going to get to why it's important in supplements in a minute. Okay, do you have any questions about the synthesis? Well, about fatty acids, basically. If not, just one last thing. We said that eicosanoids are synthesized primarily from arachidonic acid. Where is arachidonic acid in a cell? Where can we find it? Anybody? In the membrane, okay? It's going to be as a part of phospholipids. And in phospholipids, usually in membrane phospholipids, what you find is that the first position is taken up by a saturated fatty acid, generally. Okay? The second position is usually taken up by a polyunsaturated fatty acid, such as arachidonic acid. What is this X? Huh? Okay, it could be choline. What else could it be? Ethanolamine, yeah. What else? Could be choline, so we have phosphatidylcholine. We could be ethanolamine, we have phosphatidylethanolamine. What else? Come on. Inositol diphosphate, etc. Okay, so before we can actually start synthesizing eicosanoids, we need to remove arachidonic acid from the phospholipid. What kind of enzyme are we going to use for that? What kind of enzyme can we use to hydrolyze a phospholipid? Huh? Sorry, I couldn't hear that.
What did you say? Sorry.
How would you call an enzyme that we would use to hydrolyze a phospholipid? Just phospholipase, very good. So we're going to use a phospholipase. Now, you've already heard about some phospholipases, or at least one of them. Which one?
Phospholipase C.
Phospholipase C. What does it do? What does phospholipase C do? What does it do? What are the products of the reaction? Okay, phospholipase C basically hydrolyzes this bond. Okay, so it leaves diacylglycerol, and usually it's inositol trisphosphate that's left. Okay, so this is the reaction catalyzed by phospholipase C. But we need a different phospholipase because what we need is to hydrolyze this bond. Fortunately, we have other phospholipases, and we have phospholipase A1, we have phospholipase A2, and just to fill the picture completely, we have phospholipase D, which hydrolyzes this bond. Do you understand? You probably, half of you can't see it. Can you see it from the back? Yeah? Okay, so phospholipase is several different types. Phospholipase C you already know, which hydrolyzes this one. There's phospholipase D, which hydrolyzes the other bond on the other side of the phosphate group. But for us, the most important is phospholipase A2, which specifically removes the second fatty acid in the phospholipid, which is often a polyunsaturated fatty acid such as arachidonic acid. Okay, clear? Yeah? Okay, let's have a 5-minute break. Just 5 minutes, okay? We're running late a little. About the first part. Questions? No? Yep.
You go from the gamma-linoleic to the dihomo-gamma-linoleic acid.
Linolenic.
You have 2 carbons, right?
That's right.
And is that why it's called dihomo, because it's 2?
That's right.
And you create arachidonic acid from dihomo gamma.
By desaturation.
Okay.
Yeah. Anything else? No? Okay, so now let's talk about eicosanoids proper. So we're going to start with arachidonic acid, even though it's not the only fatty acid that we can use, which we're going to mention in a minute. But let's start with arachidonic acid. Now, there are 2 general pathways in which arachidonic acid can be converted into eicosanoids. One is called a cyclical pathway, or sometimes you see cyclizing, because it forms a cyclical compound. Okay? And the other one is called linear, because the products do not have a cycle inside them. Okay, so 2 pathways, cyclical, cyclizing, and the other one is linear. The first pathway is started by enzymes called cyclooxygenases. Okay, cyclooxygenase. The lower pathway, the linear pathway, is started by enzymes called lipooxygenases. Cyclooxygenase. Okay? And the other one is lipooxygenase. Lipooxygenase. Okay, I'm going to go into a little bit more detail. This is just an overview. Okay, the cyclooxygenase pathway gives rise to 2 groups of eicosanoids. One is prostaglandins that we already mentioned, and the other ones are thromboxanes. That's both from the cyclooxygenase pathway. Okay. So the cyclooxygenase pathway gives rise to prostaglandins and thromboxanes. If you want me to write it down, just say write it down. Okay. Is it the worst one? really running out of options here. Okay. Oh, come on. Prostaglandins and thromboxanes. You can find it everywhere, okay? Or you can come afterwards and have a look at it. Okay? The linear pathway, the lipoxygenase pathway, gives rise to leukotrienes and lipoxins. Leukotrienes and lipoxins. Okay, cyclooxygenase pathway, prostaglandins, thromboxanes. The lipoxygenase pathway, leukotrienes, lipoxins. There are some other types of eicosanoids as well, but we're not going to mention them. Okay, so these are the 4 groups that you need to know. The first product of the cyclooxygenase pathway is prostaglandin H2. And the first product of the linear pathway, the lipoxygenase pathway, is a hydroperoxy eicosatetraene or eicosatetraenoic acid. I'm gonna go back to it. Okay. Now, I'm going to go back to that.
Can you find the abbreviations on the internal?
Yes, you can find all of them everywhere. Yeah. Okay. Why do I mention that the first product of the cyclooxygenase pathway is prostaglandin H2? The only reason is to show you the nomenclature of prostaglandins. Okay. So all prostaglandins are abbreviated like this. The PG stands for prostaglandin. Okay. It's not specific to anything. The letter, which could be E, F, G, H, and some other one, I, says something about the structure, about how the molecule is put together. Okay, so you don't need to know that. It's just how it's actually, yeah. What is the structure of the prostaglandin? The number tells us which fatty acid we started from. So number 2 means that we started from arachidonic acid. Okay? Okay? If we start with the other polyunsaturated fatty acid, the omega-3, which I mentioned, the EPA. Okay? Remember EPA? Eicosapentaenoic? We're going to get PGH3. So it's going to be a class 3 of prostaglandins. They all look very similar, but we start with different fatty acid. Okay? You don't have to remember that. I'm just trying to explain to you how the nomenclature works, that if you need to know it, you'll know how it's done. Okay? If we start with another 20-carbon polyunsaturated fatty acid that I already mentioned, which is dihomo-gamma-linolenic acid, also has 20 carbons. Okay? Remember? Then we make PGH1. Okay? So the group of prostaglandins would be class 1. Why is that important? Because the different classes of prostaglandins have different effects. Okay? So prostaglandins from the 2 series are sometimes going to have a stronger effect on something and a weaker effect on something else than, for example, the 3 series, which is derived from EPA. And that is the reason why it's recommended to eat fish oils or EPA in supplements as a protection from myocardial infarction and some other cardiovascular diseases. Because the prostaglandins and thromboxanes as well, produced from EPA, have weaker effects on blood coagulation and platelet aggregation than the ones that are derived from arachidonic acid. Does it make sense? So if we supplement at least some of our phospholipids with EPA instead of arachidonic acid, we are going to produce prostaglandins and thromboxanes derived more from EPA, and they have different effects in our body, which is actually more beneficial and decreases the risk of myocardial infarction. Okay? So we can make prostaglandins from 3 different acids. We can make them from arachidonic acid, we can make them from EPA, or we can make them from dihomo-gamma-linolenic acid. Okay? They have different effects. Right. Okay, so that's just about the nomenclature itself. what are the effects of all these, well, at least these 4 groups of eicosanoids? Prostaglandins, as we mentioned, are major mediators of inflammation. So they mediate fever, they mediate, to some extent, they mediate the swelling, they definitely mediate the pain of inflammation. So all these things increase permeability of capillaries, etc. So these effects, these symptoms of inflammation are mediated primarily by prostaglandins. Okay? Fever actually is also mediated by prostaglandins, but it's slightly more complicated way. Because all the other, if you have a localized inflammation, all the effects of prostaglandins actually happen in the place. But fever is actually created by prostaglandins in the brain. Okay? So for the initiation of fever, prostaglandins need to be synthesized in the hypothalamus, where they change the setting of the thermostat, of the body's thermostat, and increase body temperature. Okay? So this is also mediated by prostaglandins, but not locally, but in the brain. Okay? Thromboxanes, I mean, there are many other effects of prostaglandins. For example, which have nothing to do with inflammation. So for example, prostaglandins are responsible for the regulation of mucus production in the stomach. Why is it important to produce mucus in the stomach?
To protect the walls
Indeed.
of the stomach.
Exactly, to protect the walls of the stomach from being digested by the gastric juice. Okay, it's extremely important, and this is also regulated by prostaglandins, so we need prostaglandins for that. Prostaglandins are very important for the regulation of blood flow in kidneys. So if we interfere with prostaglandins, we can have kidney problems. Okay, so prostaglandins have many different functions. Thromboxanes are very important for the aggregation of platelets, which are important for blood coagulation. Okay? So thromboxanes, platelet aggregation, and that's the reason why we said that different fatty acids can actually protect us from myocardial infarction, which starts usually by platelet aggregation in the coronary arteries. Okay? Leukotrienes from the linear pathway are mostly responsible. Yeah, actually another thing. While cyclooxygenases can be found in most tissues, lipoxygenases are mostly in immune cells, in white blood cells. Okay, mostly, not entirely, but mostly. Leukotrienes have been found to be important for the development of asthma attacks. Okay, so they regulate bronchial airflow, and they are a big part of the inflammation in asthma. Okay, lipoxins. Well, I'm not going to go into details. They are important for inflammation as well, for the mediation of inflammation. Okay, also for the resolution of inflammation, so for the repair of the tissues. Okay, so these are the functions. Do you have any questions about, this is all I'm going to say about the synthesis of eicosanoids. It's extremely complicated. There are many different eicosanoids and different structures. It's a nightmare, so I'm not going to go into any more detail. Yeah?
Could you just repeat the things you said about, for example, thromboxanes, important for platelet aggregation?
Yeah, okay, yeah, so that you repeated. I mean, leukotrienes are, from a clinical point of view, are important because they're involved in asthma, in a type of asthma attacks. Okay, basically the inflammation of the lungs, of the bronchi in asthma is mediated to a large extent by leukotrienes. Lipoxins also play a role in inflammation, but also in the resolution of inflammation. So you have something inflamed, and then you also need to regulate how you're going to remove all the white blood cells, how you're going to repair the tissue. And lipoxins are very important for that. Okay. Now this is a super extremely brief overview. Okay. The effects are very complex. They depend on which specific prostaglandin, or which specific thromboxane, or which specific leukotriene we're talking about. Okay. So this is kind of a really, a bird's eye view of the problem. It's much more complicated than that, but you don't really need to know that unless you become immunologists or anything like that. Okay? Yeah. Right. Yep.
Which cell synthesizes this product? Is it like
Okay. Prostaglandins can be synthesized by almost any tissue in the body. Okay. Thromboxanes are mostly synthesized in the endothelium and in platelets. Leukotrienes and lipoxins are mostly synthesized in white blood cells. Okay. So these are more specific to immune system, while these not so much. Okay. Okay. Well, if there are no more questions about this, let's move on to the actual treatment of inflammation. What kind of methods we can use to treat it. At the start of the lecture, we talked about aspirin, and we said that until 1970s, we had no idea what aspirin actually did, what the mechanism of effect was. And then we said that in the late 60s and 70s, people discovered that it inhibits the production of prostaglandins. And the inhibition is at the level of cyclooxygenase. So aspirin is a cyclooxygenase inhibitor. And actually, when I mentioned the whole group, well, you mentioned the group of non-steroidal anti-inflammatories, non-steroidal anti-inflammatory drugs are all, their main effect is by inhibition of cyclooxygenase. Okay? They're cyclooxygenase inhibitors. Now, as I said, it's actually when you interfere with the production of prostaglandins, or thromboxanes for that matter, by inhibiting cyclooxygenase, you can actually cause problems. Because prostaglandins are not just involved in inflammation, they're also involved in other processes. Well, fortunately, there are two types of cyclooxygenase, and each of them specializes to only certain types of prostaglandin production. There's COX-1, there's COX-2.
Can you just repeat what it can also cause?
That it causes problems because since prostaglandins regulate, mucus production in the stomach, then obviously if we inhibit it, we can cause problems, right? So there are two isoenzymes of cyclooxygenase, and most non-steroidal anti-inflammatories are non-specific, okay? So they just inhibit everything, including aspirin. Aspirin inhibits both isoenzymes basically in the same way, okay? Also, just one second, also aspirin is the only irreversible inhibitor of cyclooxygenase. All the other ones are reversible, they're competitive, okay? But aspirin is irreversible. What it actually does, it binds into the enzyme and it releases the acetyl group, which then remains, so it acetylates the enzyme, which inhibits completely its function, okay? So aspirin is irreversible, the other ones are reversible. Yeah, there was a question?
Was it generally that all COX inhibitors are non-specific? Or
Basically all of them, but I'm going to mention the ones that are specific, okay? But generally they're non-specific. Do you know any other non-steroidal anti-inflammatories except for aspirin? Okay, diclofenac, yeah. Ibuprofen, yeah. All these ones, indomethacin, whatever you get prescribed by a doctor if, you sprain your ankle or something, it's probably going to be a non-steroidal anti-inflammatory. So there are two isoenzymes that are both inhibited by most non-steroidal anti-inflammatory drugs. COX-1 is generally considered as like the good COX enzyme. So it's the enzyme that produces prostaglandin for housekeeping functions, such as production of mucus in the stomach, for the regulation of blood flow in kidneys, etc., etc. Okay? So COX-1 is a constitutively expressed enzyme in many different tissues. And its main function have nothing to do with inflammation, okay? COX-2, on the other hand, is what sometimes people call the bad enzyme. So it's the one that is involved in inflammation. It's not constitutively expressed, it's inducible. So only when it's needed in inflammation, the production of COX-2 increases, okay? So this one's constitutive and housekeeping. This one is connected to inflammation and is inducible. So obviously, once this was discovered, which is actually a relatively recent discovery, I think late 80s, early 90s, the pharma companies started to look for COX-2 inhibitors, for specific inhibitors of COX-2, because obviously inhibiting COX-1 only causes side effects. Okay, what is the main side effect of non-steroidal anti-inflammatory drugs? Does anyone know?
Ulcers?
Yeah, gastrointestinal bleeding and gastric ulcers. Okay, obviously because it inhibits, makes sense because it inhibits the mucus production, okay? So number one side effect, there are other ones, but number one side effect is gastrointestinal bleeding. So what they thought, what the pharma companies thought, well, we're going to produce COX-2 inhibitors that are going to be at least as good, if not better, anti-inflammatory drugs, but they won't have the side effects. Okay? And indeed, in mid-90s, they produce a series of drugs that all end with coxib. So that's how you recognize them. Okay? Like celecoxib or rofecoxib, etc. Okay? Coxib standing for COX inhibitor. Okay? And these are fairly specific, or very specific in some cases, COX-2 inhibitors. Okay? It was a huge revolution, and everybody thought, okay, this is the end of these traditional non-selective ones. But actually, there were problems, and there still are problems with these drugs. First of all, most of them weren't really all that effective, okay, for some reason. They actually weren't that good. And the other problem was that in some of them, there were very, very, very serious side effects, such as cardiovascular mostly, such as myocardial infarction. So people who were taking it were actually dying of heart attacks. It was a big story. Rofecoxib was actually withdrawn from the market, and celecoxib, which is still marketed, it has a big warning on it, at least in the US, which says that, be careful, it causes serious side effects. There was a huge promise in COX-2 selective inhibitors, which actually didn't really translate into any practical benefit. Now COX-2 inhibitors are only used pretty much only in patients that do not tolerate the traditional non-selective ones, because they are much more expensive and they cause actually significant side effects themselves. The whole story of especially rofecoxib and some of the other coxibs is actually very interesting, because it actually came out that the pharma companies who produce them, I mean, rofecoxib was marketed as Vioxx. In case you look for it for the history, Vioxx, it was actually known as Vioxx. It was a big scandal. Because the company who marketed it, I think it was Pfizer, I'm not sure, they actually knew about the side effects. They knew that it caused those side effects, but they marketed it anyway. And it killed a lot of people, and they had to pay huge amounts of money when they withdrew it. So, and I think there were problems with celecoxib where they actually fabricated some of the efficacy numbers, so it looked like it was more effective than it actually was. So it's a very interesting story of how pharma companies these days work and how they deceive. So if you want to read about Vioxx, it's a very interesting story. Right. So there do exist COX-2 inhibitors, selective. Not that great. Yeah?
And why did they cause these side effects?
Yeah, that's a very good question. I'm not sure it's really well known, but the problem is that prostaglandins, both prostaglandins and thromboxanes, are necessary for the balance of platelet aggregation and blood clotting. And probably they disturb this balance in a different way than the classical ones. So the classical NSAIDs, and especially aspirin, actually are beneficial. And you may know that a lot of older people take aspirin in very low doses as a prevention of myocardial infarction. But these ones clearly cause the opposite by just pushing the balance the other way. Okay, so that's probably the explanation. Right. Just one other thing when we're talking about adverse effects of these drugs. Remember that we said that arachidonic acid can undergo, basically, can enter two pathways. One is the cyclooxygenase pathway, and the other one is the lipoxygenase pathway. Now, if you block cyclooxygenase, what happens is that obviously a lot of arachidonic acid is left over because it's not being used for the production of prostaglandins. And this available arachidonic acid can then be used in much higher numbers, in much higher amounts, to produce leukotrienes and lipoxins. And this is the reason why there's another side effect of non-steroidal anti-inflammatories, and especially aspirin, and that's asthma. It's relatively rare, so not a lot of people get it, but there is a fairly substantial number of patients who can, if you give them aspirin, especially aspirin, who can have an asthma attack. And the reason is that basically the arachidonic acid that is not used for prostaglandins is shunted into the production of leukotrienes, which can start asthma. It doesn't happen in everyone, but in some susceptible patients, this can happen. Okay, so another side effect. Okay, any questions about non-steroidal anti-inflammatories?
Why we should not give fever. It's really said, no, don't give it to you.
That's another interesting story that I'm not sure we can spend time with. It's because of an extremely rare syndrome, which is called Ray's syndrome, which was observed. It's very, very rare. It's deadly. It's very serious, but it's extremely rare. It happens in small children who have fever. Nobody really understands what happens. And there were some studies that linked the occurrence of Ray's syndrome to aspirin. But later on, it was found that actually it was more association, that basically because everybody was taking aspirin for fever, that it may not actually have played a causal role. I mean, I'm no expert in Ray's syndrome, and it's an extremely rare condition. So, but the reason is that, so now people say, well, maybe it's not a good idea to give aspirin to children. And actually, most people, nowadays don't really take aspirin when they have fever or anything. They usually take ibuprofen or paracetamol. And that's part of the reason they kind of feel, aspirin is kind of associated, they could do something bad. But I don't think the data is actually very strong on that it causes Ray's syndrome. Well, talking about paracetamol, that's another very interesting. Paracetamol. Paracetamol is actually a very, very old drug. It actually predates aspirin. It's quite interesting. But it actually didn't go into wide use until about 1950s or 60s. Because until then, actually similar to aspirin Ray's syndrome, it was connected to a very serious side effect. Actually, it was methemoglobinemia, but anyway. But then it was found out that actually it wasn't paracetamol that was causing it. But the side effect was observed in the 19th century, and basically nobody wanted to use it for 50 years later on. And then they found out that actually it wasn't paracetamol that caused it, and suddenly paracetamol is extremely widely used because it has basically no side effects whatsoever. However, paracetamol is not a non-steroidal anti-inflammatory drug. Okay? It doesn't have anti-inflammatory properties. So it decreases fever, it decreases pain, but it's not considered anti-inflammatory. The mechanism of effect of paracetamol is still not understood. Okay? There was a hypothesis that it inhibits a third kind of cyclooxygenase, COX-3. But as far as I know, it's really unclear, and it's very, people still don't understand what it actually does. And there are probably some other kinds of effects as well. Paracetamol, as I said, has basically no side effects when given in proper doses, but in very large doses, it is extremely toxic, and it damages your liver. And people have actually committed suicides or were, unintentionally poisoned by paracetamol. But it has to be a very, very high dose. Okay, so in low doses, in normal doses, I think it's up to something like 5 grams a day or something. You're fine. But once you start exceeding that, it becomes extremely toxic, and it's very difficult to treat. There is a specific antidote for it, but anyway, let's leave that for later. Right. So those are non-steroidal anti-inflammatory drugs. Now I said that it will become clear why we call them non-steroidal. And the reason is that the next class of anti-inflammatory drugs that's extremely widely used and very effective are steroids, and specifically glucocorticoids. Glucocorticoids. Now, as you know, glucocorticoids are hormones of adrenal glands, and specifically adrenal cortex. Okay, together with mineralocorticoids. And you also know that glucocorticoids have a massive range of effects, metabolic effects, all sorts of effects in the body. Okay, they are catabolic, they decrease the synthesis of proteins, etc. They increase the breakdown of proteins, blah, 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 etc. Many other effects, but they are also extremely effective anti-inflammatory drugs. Okay? They're very good in inhibiting inflammation. And they do it basically by 2 different mechanisms. One is a direct inhibition of eicosanoid synthesis. But unlike non-steroidal anti-inflammatories that just block cyclooxygenase, glucocorticoids actually block it at the very start of the synthesis. So they block the release of arachidonic acid from phospholipids. How do they do it? Glucocorticoids increase the production, the expression of a class of proteins called lipocortins. And these lipocortins inhibit phospholipase A2. Okay, so glucocorticoids increase lipocortins in the cell, and they inhibit phospholipase A2. If phospholipase A2 is inhibited, the cell cannot produce arachidonic acid, and therefore it cannot produce prostaglandins or thromboxanes or leukotrienes or lipoxins or any of them, because there's no arachidonic acid available. Okay? So this is one effect of glucocorticoids and a major effect in their anti-inflammatory use. The other effect, which I'm not going to go into details, but that is a direct effect on white blood cells. So glucocorticoids can actually inhibit the function of white blood cells directly, which is less of an anti-inflammatory effect, and it's more of an immunosuppressant effect. Okay? So glucocorticoids are also immunosuppressant. Now, yeah?
So can you just repeat the glucocorticoids? What do they do with the white blood cells? They inhibit? Or?
Yeah, they inhibit the function and the proliferation of white blood cells, especially lymphocytes. They also do something with neutrophils. But,
yeah, so
yep.
can you also repeat what they increased to inhibit the...
So they increase the production of lipocortins. It's a class of proteins that inhibit phospholipase A2. They also do other things, but yeah. Okay, so glucocorticoids, extremely effective. Nowadays, we don't obviously use cortisol, which is the natural glucocorticoid, but what we use are super highly effective fluorinated and different derivatives that are 10,000 times more effective than cortisol. The problem with glucocorticoids, and the reason why it's not something you just buy over the counter for your headache or something, even though it would probably work, is that they have huge amount of side effects. And the reason is that we cannot actually separate their anti-inflammatory effects from all the other effects that they have in the body. Okay? So if you take glucocorticoids as anti-inflammatory, those glucocorticoid drugs, those derivatives, will have all the effects of normal glucocorticoids, only amplified 10,000 times. Okay? So you will get, decreased muscle mass, more production of fat, etc., all these things. So the problem with glucocorticoids, extremely good anti-inflammatory, it's much better than non-steroidal, but they also have huge side effects. So you have to choose very carefully if it's worth using it. But it's used obviously for more serious inflammations than, that just your knee hurts a little bit, then you wouldn't use glucocorticoids for that. And if you would, it probably would be local, so you would just get an injection of glucocorticoids into the knee rather than systemic. Right. Now, we moved from non-steroidals, which are reasonably effective but very few side effects, to glucocorticoids that are extremely effective but actually quite a lot of side effects. And now we're going to move to another group of drugs that are pretty effective, but actually the side effects are very serious, and those are immunosuppressants. Okay, so once again, you wouldn't use an immunosuppressant if you had a localized small inflammation, because there's no point. You wouldn't want to inhibit the function of the immune system in order to just resolve one inflammation. And sometimes it would be actually counterintuitive. You wouldn't want to do it if there is bacterial infection. You obviously wouldn't want to suppress the immune system. But as you know, there are many kinds of inflammation, and some of the chronic kinds of inflammation, there is basically no other way. We need to inhibit the function of the immune system in order to save the patient. And a typical attack of the immune system against, well, not quite its own tissues, but the situation in transplantations, in organ transplants, is that you have to use immune suppressants to stop basically the attack of the immune system against the transplant, the new organ, which is a kind of inflammation. Okay, so immunosuppressants are used, for example, in organ transplants to basically lower the ability of the immune system to attack. The best known immunosuppressants are cyclosporin A. Now you will find the spelling with Y here as well. Okay, this is the correct international spelling, cyclosporin, but you will find Y here as well. Okay. It's quite widely used, but this is the correct one. And the other one I just want you to kind of know the name of is tacrolimus. Tacrolimus. So these two are immune suppressants that are used especially in organ transplants, okay, to lower the... yeah, question?
Do you have to use them all your life after?
Yes, after the transplant you basically have to use them indefinitely. Yeah. Okay, so these are the most widely used immune suppressants, especially in organ transplants. But sometimes you need to suppress the immune system even when no external tissue is present. So in autoimmune diseases, sometimes the attack, the inflammation that your immune system is committing against your own tissues is so severe that, sometimes you use glucocorticoids, but sometimes you have to use something even more effective. And what sometimes is used for that are cytotoxic agents. Because remember when we talked about the cytotoxic therapy, about anti-cancer drugs, that many of them have, as a side effect, they have suppression of immune function, suppression of white blood cell function and bone marrow. So what is often used is methotrexate. What is the mechanism of effect of methotrexate? Anybody? Yeah, it's an antifolate, okay? So it blocks the metabolism of folic acid. So you can use methotrexate not to treat cancer, but to inhibit the functions of our own immune system if it really is attacking our own tissues, okay? So in some types of autoimmune diseases, you can use methotrexate to stop the inflammation, okay? It's questionable whether to call methotrexate an anti-inflammatory drug, but basically it's used to stop inflammation as an immune suppressant. Okay. That's pretty much what I wanted to talk about. Do you have any questions? Yeah?
Will they inhibit the production of gluten-free eicosanoids?
Could you just repeat the beginning?
Glucocorticoids, will they inhibit the production of
Yeah. So the question is whether glucocorticoids will block the production of other classes of eicosanoids from like EPA. Yes, they will. Because the same way that arachidonic acid is put into phospholipids, the same way EPA or dihomogamma-linolenic, there is no other way to get them. It has to come from phospholipids, okay? Those fatty acids don't just float around the cell, they are in phospholipids. So yes, glucocorticoids will inhibit all of them, yeah. There was another question somewhere here, no? Okay, well, if there are no more questions, that's it for today.